Since 1929, we have known that we are made of chemical elements forged in the centers of stars. By 1957, the understanding of our connection to the universe had deepened significantly. The sky isn't just pretty to look at. It serves as a window to the incredibly powerful universe we live in. There's so much happening beyond our planet that we are usually oblivious to. Why are we here? Why do we have stars and galaxies? It could have been something else entirely. Yet, even when these cosmic phenomena affect us, we tend not to pay attention until things get serious. This might be the case now. Betelgeuse has long been one of the brightest stars in the night sky, but it has recently begun to behave unpredictably, vibrating violently, and something terrifying may be unfolding. Betelgeuse isn't just an ordinary star. It's one of the largest stars ever discovered, with a mass roughly 20 times that of our Sun. From our vantage point on Earth, Betelgeuse might seem like just another distant star, but it is actually a supergiant with a status far more significant than its appearance suggests. Located more than 640 light-years away, this might seem like a trivial distance, but in cosmic terms, it's monumental. Even if we could travel at the speed of light, it would still take over 640 years to reach Betelgeuse. Under normal circumstances, it would take more than 12 million years, a time frame longer than the entirety of human civilization on Earth. The immense power of Betelgeuse is reflected in its behavior. We often think of stars as calm, stable objects, but Betelgeuse challenges this notion. It's always been a pulsating red supergiant, known for its fluctuations. When it expands, it appears brighter. When it contracts, it becomes dimmer. These fluctuations in luminosity occur over extended periods ranging from tens to hundreds of days. What's even more interesting is that Betelgeuse's brightness varies widely, with the shortest cycle lasting around 185 days and the longest extending up to 2,335 days. In February 2021, Betelgeuse registered one of its lowest V-band magnitudes in recent years at plus 1.614, marking a significant departure from its usual brilliance. Betelgeuse's reddish hue comes from its cooler surface temperature of around 3,500 Kelvin, notably cooler than our Sun's 5,500 Kelvin. Despite being much larger, Betelgeuse appears dimmer because of its lower energy emission per unit of surface area. This giant star has remained relatively stable for most of its life, even with its pulsations. However, the recent changes have raised concerns. One explanation is that Betelgeuse's helium shell is burning as it moves through its stellar life cycle, gradually depleting its hydrogen core and converting it into helium. As hydrogen fusion slows down, the star's outer layers expand, causing it to swell in size and transition into the red giant phase. During this phase, helium accumulates around the depleted core, and the intense heat initiates a secondary fusion process, known as helium shell burning, creating heavier elements like carbon and oxygen. Helium shell burning isn't as stable as hydrogen fusion, leading to periodic energy buildups and releases. These fluctuations cause the star's outer layers to expand and contract, manifesting as pulsations and affecting its brightness. The energy generated during this process can create strong stellar winds, which carry away mass from the star's outer layers, contributing to its evolution. The rhythmic pulsation of Betelgeuse's outer layers acts like a heartbeat, observable as changes in its luminosity. While this might explain some of Betelgeuse's recent behavior, more evidence is needed to confirm this theory. Astronomers use various techniques to study pulsating stars like Betelgeuse. Photometry monitors the star's luminosity changes, while spectroscopy analyzes its light spectrum to understand temperature, composition, and motion. Spectral changes during pulsations offer insights into the conditions within the star's outer layers. Computational models also simulate Betelgeuse's internal dynamics, helping scientists predict its behavior. This synergy between observational techniques and computational models paints a clearer picture of Betelgeuse's pulsations. Stellar convection, the movement of matter in response to temperature differences within a star, might also be influencing Betelgeuse's behavior. Hot material rises toward the surface, carrying energy, while cooler material sinks toward the core. This creates convection currents that transport energy to the star's outer layers. These dynamic flows can lead to fluctuations in the star's brightness and contribute to its pulsations. Another possibility is that Betelgeuse could be part of a binary star system, where material transfer between two stars can cause instabilities and initiate pulsations. In such systems, gravitational interactions can pull material from one star to another, profoundly impacting their evolution. The recent changes in Betelgeuse's behavior could be linked to this process, suggesting that it might have a companion star influencing its activity. Understanding Betelgeuse's pulsations and recent changes is crucial, as it helps scientists piece together the life cycles of supergiant stars and their eventual fates. Whether these fluctuations signify an imminent supernova or just temporary instability, one thing is certain: Betelgeuse's activity is a fascinating glimpse into the complex and dynamic nature of our universe. As material flows from the donor star to the recipient, a few key processes occur. The influx of mass onto the recipient star can significantly impact its structure and behavior. As the added material increases the recipient star's mass, it alters internal pressure, temperature, and nuclear fusion processes. These changes can trigger pulsations within the recipient star. What happens here is that the rapid structural alterations induced by the inflow of material disrupt its equilibrium entirely, leading to instabilities that manifest as pulsations. The star's outer layers may expand and contract rhythmically, generating fluctuations in luminosity. These pulsations arise from the star's attempts to find a new balance between the forces at play: gravity, radiation pressure, and internal nuclear reactions. All of this can significantly impact the evolutionary paths of stars within binary systems, potentially altering the recipient star's evolution and leading it down a different trajectory than if it were a single, isolated star. Throughout historical studies, even supergiant stars have typically been considered as individual celestial bodies. It wasn't common to explore how two stars interact, let alone how one can transfer energy to another. But this is not just a theory. This phenomenon has been happening throughout space for centuries, and recent advances in telescopes and research have allowed us to understand these interactions in unprecedented detail. One common explanation for the pulsating effect in stars has been proposed for a long time, but it may indicate something more alarming. The star could be nearing a supernova explosion, which would result in catastrophic consequences. For example, Betelgeuse is currently in the later stages of its life cycle. Like other massive stars, it has maintained a delicate balance between the inward pull of gravity and the outward pressure generated by nuclear fusion reactions at its core. However, this balance is not permanent. As Betelgeuse consumes its nuclear fuel, the equilibrium gradually shifts. Over time, the availability of hydrogen fuel decreases, affecting the core's energy production. With less fuel, the core's energy output diminishes, weakening the outward pressure and causing the core to contract under gravity's pull. This contraction leads to a rise in temperature, compressing matter further, and triggering a new phase of nuclear fusion. The core becomes hot enough to enable the fusion of heavier elements like helium and carbon. As these reactions progress, even heavier elements are created, culminating in the formation of an iron core. Iron is unique in that it requires more energy to fuse than it releases, disrupting the energy balance maintained by previous fusion reactions. Consequently, the iron core loses its ability to generate sufficient outward pressure, leading to a gravitational collapse. This collapse would trigger a supernova explosion, where the outer layers of the star are expelled at extraordinary speeds. For observers on Earth, Betelgeuse's supernova would appear as a spectacular burst of light that might last for days or weeks. The event would release an immense shockwave that could easily tear apart the star's structure, throwing its outer material into space at incredible velocities. The release of energy during a supernova often rivals the brightness of an entire galaxy. For a brief period, this event can outshine countless individual stars in the surrounding region. Such a supernova explosion would not only provide a visually stunning light show, but also offer valuable scientific insights into the extreme physical processes during a star's final moments. Given that Betelgeuse is approximately 600 light-years away from Earth, a supernova explosion would be visible to us. However, if it were closer, the consequences could be devastating. Gamma-ray bursts, GRBs, associated with certain types of supernovae involving massive stars could have catastrophic effects. A direct and powerful GRB could disrupt Earth's ozone layer, reducing its ability to block harmful ultraviolet radiation. This could lead to increased rates of skin cancer, ecological disruptions, and potentially devastating impacts on agriculture and food security. The electromagnetic pulses, EMPs, generated during a supernova could disrupt or damage electronic systems, communication networks, and power grids, affecting everything from consumer electronics to critical infrastructure like hospitals. The interconnectedness of modern technology means that these disruptions could have cascading effects, leading to widespread power outages and a breakdown of essential services. Moreover, the radiation and energy released during a supernova could alter weather patterns, temperature anomalies, and atmospheric chemistry, potentially leading to short-term environmental and climate changes. In extreme cases, altered weather patterns could impact ecosystems, agriculture, and food supply chains, posing significant risks to global food security. In space, a supernova could accelerate cosmic rays, posing a radiation hazard to astronauts and increasing the risk of radiation exposure during extended missions, such as those to Mars. Cosmic rays can interfere with electronic components in satellites and spacecraft, potentially affecting astronomical observations. But the consequences don't stop there. Massive stars like Betelgeuse can also turn into black holes post-supernova. This process involves the core collapsing past a critical density, leading to the formation of a singularity surrounded by an event horizon, where gravitational forces overcome all others, resulting in the creation of a black hole. Such an event would reshape the cosmic environment around it, influencing nearby stars and planets. While Betelgeuse's supernova is not expected to pose a direct threat to Earth due to its distance, it serves as a stark reminder of the violent and dynamic nature of our universe. The boundary beyond which nothing, not even light, can escape the black hole's gravitational pull is known as the event horizon. If Betelgeuse were to become a black hole, its appearance to distant observers would remain largely unchanged until they interact with the event horizon. Unlike a supernova, which generates a burst of light and energy, the formation of a black hole might not result in an immediate observable event. Instead, the transition could be relatively subtle, almost silent. However, if this event happened close to us, things wouldn't be silent. They'd be deadly. For starters, the gravitational pull of a forming black hole would unleash extreme tidal forces on surrounding objects. These forces would be much stronger than anything experienced on Earth. Nearby planets, moons, and asteroids could be torn apart or disrupted by the intense gravitational gradient, leading to fragmentation and potential collisions. The massive black hole's gravity would also perturb the orbits of neighboring celestial bodies, potentially causing planets and other objects to have their orbits altered, leading to chaotic paths, collisions, or even ejections from the solar system. As Betelgeuse collapses into a black hole, surrounding matter could be drawn towards it, forming an accretion disk. This disk would heat up and emit intense radiation across the electromagnetic spectrum, including X-rays and gamma rays. Such radiation could damage the atmospheres of nearby planets and significantly impact any organisms or ecosystems present. The formation of a black hole involves the release of high-energy particles and radiation, which could pose a threat to technology, satellites, and even spacecraft passing through the vicinity. Delicate electronic systems could be disrupted or damaged by the intense radiation emitted during the transformation. The gravitational field of a massive black hole is immensely strong due to its extreme density and compactness. If a black hole were to form from a star like Betelgeuse in the vicinity of our solar system, its gravitational influence could have significant effects on the orbits of distant objects, such as planets, asteroids, and comets. The gravitational force exerted by the black hole would pull on nearby objects, altering their trajectories and potentially causing them to deviate from their original orbits. The delicate balance of the solar system's orbital dynamics, which depends on gravitational interactions between its various components, could be severely disrupted. The introduction of a massive black hole could lead to objects being flung out of the solar system, colliding with each other, or even falling into the black hole itself. Orbits that were once predictable and stable could become unpredictable and chaotic under these strong gravitational forces. The rearrangement of orbits could have ripple effects throughout the solar system, impacting gravitational interactions and affecting the overall stability of the system. While the sun's gravity would still play a dominant role, the presence of a massive black hole nearby could introduce new gravitational interactions that destabilize the entire solar system, which could mean a complete collapse of life as we know it. The good news is that Betelgeuse is quite far from Earth. It's likely that when the star does go supernova or ends up turning into a black hole, most of us won't even know what's happening until things settle back to normal. But what do you think? Will it be a supernova light show or a destructive black hole? Let us know in the comments below. If you like this video, please give it a thumbs up, and as always, we'll see you in the next one.